Okay. So today we're going to continue our look at partial derivatives, and we are going to talk about how to compute them algebraically. And that turns out to be really, really straightforward. So remember, the idea of the partial derivative is, okay, we've got two input functions. So what we do is we keep one fixed and we vary the other. And we see how the function changes with respect to that variation. Well, if we're fixing something, that means for the process that we're doing of taking the derivative, we can treat it as a constant. So, for example, we know that if, for example, we had a function cx squared right, if we take the derivative of this is just the normal derivative that we're talking about, the answer would be 2cx. Right, the only thing that's varying is the x, then the derivative of x squared is 2x. This is a multiplicative constant, so it just stays there. This is an additive constant that just goes away. Okay, so let's have a look at this guy. Okay, so if we do the partial derivative with respect to x, then we're going to treat y as a constant and x as the varying. So the derivative of the x is 2x. The y, that y there is a multiplicative constant, so it stays. That is an additive constant, so it goes away. And so that is the partial derivative with respect to x. The partial derivative with respect to y, okay, now we change, we go 90 degrees. We think of y varying and x squared being the constant. So the derivative of this then with respect to y is x squared. Because if x is a constant, x squared is a constant. Y, the derivative of this is 1. And that's the whole shebang. So that's the whole point of today's class. It's just sort of going over and we're just kind of emphasizing that point right there. So you just treat one variable as varying and the others as a constant, and we just take the derivative like we would with just one variable varying. So this is still a function of x and y. So then I could say, well, f of x, say f of 2, 3. I just plug in, right? I plug in 2 for x and 3 for y. So 2 for x, so this becomes a 4 times a 3 is 12, plus a 3 is 15. Fx at 2, 3, again, I just plug in the numbers. 2 times 3 is 6, times 2 is 12. Fy 2, 3 is 5, right? It's 2 squared plus 1. What does this mean? It means what it always means. This is the value of the function. So when the input is 2 x's and 3 y's, our function is 15. 15, whatever it is. This and this tell us the rate of change. So it tells us that at the point 2, 3, we're thinking we're out on a map. We're thinking the height is 15, so it's measuring whatever it's measuring. In the x direction, So let's say this is the x direction. The rate of change is 12. So that means it's going up. So I'm looking there, I'm seeing a steep path up there. Okay, so if I was to increase x by 1, I would think that the function increases by around 12. Right, so I estimate that f of 3 is approximately 27. So I'm at 15, up there is 27. In this direction, the y direction, it's still increasing, but it's not as steep. In that direction, the slope is 5. So in that direction, the slope is 12. In that direction, the slope is 5. So it kind of looks like that. So if you think of yourself in a terrain, there's something steep there, there's something going up, not quite as steep. And that's how you think about it. So I would think that f of 2, 4 would be around 20. That's just my approximation using the derivatives. Okay, so let's do a kind of more concrete example. So again, let's think of again, we like this thing about the concentration of drug, right? We're injecting a drug into a body, and we think of the concentration x and t. This time, x is going to be the dose. So let's say in grams. T is going to be the time. Let's say it's in hours. And this is kind of like going to be a surge function. Like this. Okay. So what is C of 1, 2? C x of 1, 2, CT of 1, 2. Let's find these quantities and interpret what they mean. Okay. So what does 1, 2 mean? What does 1, 2 refer to? Well, we look at x is first, t is second. So 1, 2 means that we gave someone a dose of 1 gram of medicine, and we're looking at them 2 hours later. Okay, so C 1, 2 would be T is 2, so it's T e to the minus 2. And this might be measured in something like grams per liter. I don't know exactly what it was. I didn't write that down. Okay, so that gives us a concentration of the drug in the body. Okay, so we know that concentration is going to change, okay, with the different x's and t's, right? If we give a different dose, then the amount of the drug in the body is going to be different. If we go to a different time, the amount of drug in the body is going to be different. The derivatives explain how that difference comes about, what that change actually is. So Cx, or the partial derivative with respect to x. Okay, so what happens? We treat the t as a constant, and we treat the x as the variable. So this is just taking the derivative of an exponential function. So we know that the derivative of an exponential function, right, is we write down the exponential function, This t here is a multiplicative constant. And by the chain rule, we just multiply by what comes in front of the x, and that's minus t. That's minus t squared e to the minus xt. That's just following the rules of differentiation. I then plug in 1, 2. So x equals 1, t equals 2, so it's minus 4 e to the minus 2. And what are the units? The units are going to be the units of concentration. So it's going to be grams per liter, for example, per units of x, and that's going to be per gram. So this is showing us how this quantity changes as we change x. Okay. We'll also take the derivative with respect to t. Now we treat this as the x as being a constant and the t being variable. So this means it's now a product. So we use the product rule. So the derivative of t is 1 times e to the minus xt plus t times the derivative of e to the minus xt, which would be e to the minus xt times minus x, because x is now the constant. And so that would be e to the minus xt minus xt e to the minus xt. So that is going to be, when x is, that's going to be e to the minus 2 minus 2 e to the minus 2, so it's minus e to the minus 2. So we know how to figure these things out just by taking the derivatives and plugging the numbers in. And of course, this is now going to be grams per liter per hour, right? Because we've got a different thing we're taking things with respect to. But it's the same strategy that I talked to you about before, which is that we keep one variable fixed and we look at what happens when we vary the other. So, for example, if we wanted to graph what this looked like, so we had, remember we had C to minus xt. So we could fix things, say, we could have a look at what happens when x equals 1. Okay, so when we fix x, we're saying that we're looking at the dose of just being 1 gram, and we're varying t now. So what happens to this is we're going to fix it, we're going to look at this as t times e to the minus t, right? We fix x equals 1. We know what that looks like. That looks like a surge function. Right, so for a fixed dose, the drug comes in, it increases and then it decreases. Or we could look at the other way. We could fix t. We could fix t equals 2. And what that means is we're only looking at what happens after 2 hours into the future. Okay? And so now, this is going to be a function. This is t and c. So now this is x and c. Okay, as a variable of x with a fixed t, what is it? It's fixed t, it's the function 2e to the minus 2x. That is just exponential decay. Oh, sorry, I gave the wrong thing. This isn't talking about the concentration of the drug. This is the concentration of the bacteria in your. This is like giving an antibiotic, and so this, as you increase the dose, that kills off more bacteria. But anyway, that's what it looks like. So in one direction, we've got a whole bunch of surge functions. In the other direction, we've got a whole bunch of exponential decays. And if you're good in your brain and you can picture things three-dimensionally, you can actually think of this as a landscape. Some people find it easier to think about things in three dimensions, other people don't. So if you can think of this all in one go, that's great. If you can't, then you just have to consider it piece by piece. Let's do another one. Let's have a look at an example from economics. So let's have a look at one of those Douglas-Cobb functions. Let's say you own a printing press, printing business, and you've discovered over time that your Douglas-Cobb function looks like this. So P is the production, N is your labor costs, and V is your sort of technology costs. And how much you invest in equipment and so forth. Okay, so it's just a function, right? And so again, we can ask the same kind of thing. Well, what does P of 100, 200? So let's say this is in thousands of dollars. In thousands of dollars. Okay, and so you can just kind of plug those numbers in and you'll get how much you produce. Okay. What does the partial derivatives tell us? So let's have a look at Pn. And Pn says that we're going to keep technology fixed, and we're going to see what happens when we change the amount of money that we spend on workers. Okay, so this is just a power rule. So down comes the 0.6. We subtract 1 from the thing here, so we get n to the minus 0.4. We get v to the 0.4. So we actually get 1.2 times v over n to the 0.4. Okay, and so then we can plug in our values, Pn 100, 200 equals 1.2 times 2 to the 0.4. And we look at that in our calculator. So let's say production is like thousands of whatever it is we do when you have a printing press. So what does this number tell us? This number tells us how much more production we can get for every extra dollar that we spend hiring new workers, for example. It's a useful number, okay, but it is like production per dollar on labor. For every extra dollar we spend on labor, this is how much more we get. We can do the same thing. We can think, well, am I going to spend this money on labor, or am I going to spend it on getting a new machine? Well, we take the partial derivative with respect to v. Again, down comes the power. So we get 0.8. You get n is fixed. And we subtract 1 from this, so we get v to the minus 0.6. So this is 0.8 times n on v, 0.6, which is 0.8 1/2 to the 0.6. And again, that's just a number that we look up, and that's production per dollar on capital. That means how much extra production we can get by spending an extra dollar getting equipment. Okay, so this is really not so different from what we did before when we just looked at derivatives. It's just now that we've got more inputs, we can do things kind of that way. Oh, we're still recording, great. Okay, so let's just take a couple of derivatives just to make sure we all got it. So let's have a look at a couple of functions. 3x plus 5 e to the minus 5y, for instance. X squared times y. And y squared times e to the 2x. So they're all examples of functions. And so we can take that derivatives with respect to x. What's the derivative of this with respect to x? This is a constant. It's an additive constant, so it goes away. This is just an x So it's just what is the number in front of the x? It's 3. Okay, if we just fix y and let x vary, this is just a linear function. And the derivative is just the slope. This one here, the derivative with respect to x is what? What about the y? It stays there, right? Because it's a multiplicative constant. So that's a hard thing to remember. This one, with respect to x, the y squared stays because it's just a multiplicative constant. It's an exponential, so down comes the 2. And let's do the partial derivatives with respect to y. What's the derivative of this with respect to y? What happens to this? Goes away because it's just additive. This 5 stays. It's an exponential. The derivative of an exponential is an exponential. We've got to multiply by that -5. What about the derivative of this with respect to y? It's a derivative with respect to y. So the x squared is a constant. So this is like, what is the derivative of a constant times y? Just x squared. What about this guy? With respect to y. What's the derivative of y squared? 2y. This is just a constant in front of it. So it's 2e to the 2x y. But we can do more, right? We can have second derivatives. But if you think about it, there's lots of second derivatives, right? We can take the derivative of x twice. Okay, what's the derivative of this with respect to x? Just 0, yep. Derivative of this with respect to x? 2y, yep. The derivative with this with respect to x? It's just an exponential, so it just keeps on being the same. Every time we take a derivative, we're just multiplying it by 2. Then we can take the derivative twice with respect to y. Okay, so what happens when we take the derivative of y of this? Yeah, it just multiplies by -5. What's the derivative with this respect to y? Nope. X squared is a constant. 0. Okay. This is hard. Keep on. You got to go from one instant you put it as a constant, and now it's a variable. This with respect to y. Yep. But now there's a new kind of derivative. We can take the derivative with respect to y And then we can take the derivative with respect to x. Okay, so what's the derivative of this with respect to x? 0. Or we can take the derivative with respect to x and then the derivative with respect to y. So what's the derivative of this with respect to y? 0. Okay. What's the derivative of this with respect to x? 2x. What's the derivative of this with respect to y? 2x. How are we going? The derivative of this with respect to y. Yep. 4y e to the 2x. And the derivative of this with respect to x. Okay. Whew. That's a lot of derivatives. Okay. One thing to notice, they're the same. And so that's always going to be the case. So you don't have to worry about what does this mean? Does this mean doing x first or doing y first? Because it comes out to the same answer. That's known as the equality of mixed partials. Whew. Okay. That. Okay, so that's what I was talking about. That was the point of this exercise here. Right, so we get second order partial derivatives. So if there's 2 inputs, that means that there's 4 partial derivatives. Okay, so you've got like 2 choices for the first, 2 choices for the second. So 2 times 2 is 4. And you see that goes up ridiculously a lot, right? So if you had 3 inputs, then there'd be 9 different. So that's why we don't bother with that. But the nice thing is we've got this equality of mixed partial derivatives, which quite often makes life easier for you. Okay, so here's a nice complicated function. Which of the following are the 2 partial derivatives of f? So which is going to be the easy one to do? It's going to be defining the partial derivative with respect to y, right? Because it only appears in there once. Okay, so the partial derivative of y is going to be the x squared stays as a constant, multiplicative constant. What's the derivative of ln? It's just 1 over, right? So it's 1 over x squared y, and then you've got to multiply by the derivative of x squared. So can anyone do that in their head? What is it? We've got x squared ln squared y. X squared, 1 over x squared y times the derivative of x squared y. Oh, no, sorry. Times the derivative of y, which is x squared. Yes. Right, because we're taking the partial derivative with respect to y. So which one of those is the answer then? It has to be C or D, right? So what's the partial derivative of this with respect to x? What do we have to use? Chain rule. So we need to have an x. So we have to have 2x times ln of x squared y. Okay, so that doesn't do us any help because that's in both of them. Plus x squared times the derivative of this with respect to x. So what's the derivative of ln? 1 over. Now we're going to take the derivative of this with respect to x. What's that? 2xy. Right? And so what do we get? These cancel, these cancel. We're left with this one. We're left with C. Okay, so once we have derivatives, we can have differential equations, where differential equation what does it mean to solve an equation? Okay, so let's write down an equation. X squared plus 2x plus 1 equals 4, for example. I say x equals 1 solves this equation. What do I mean by that?
Both sides they cancel out, x plus equal 1.
You plug in x equals 1, what do you get?
0. Well, 4 will cancel out.
Well, you'll get 4 equals 4.
Yeah.
Okay. That's what you meant doing everything.
Yeah.
Okay. Sure. That's one way of doing it. But the way I think about it is I plug in x, I get 4 here, I get 4 here. That's a true statement. So therefore it's solved. That's what I mean by solved equation. It makes a true statement. X equals 0 does not solve. Why is that? Well, when I plug in x equals 0, I get 1. I get 1 equals 4. 1 equals 4 is a false statement. So I'm just talking about this in terms of logic. So that's what it means to solve something. You solve something if you come up with truth, right? And you don't solve it if you come up with false. So you can do the same thing, not just with numbers, but you can do it with functions as well, right? So this is an equation where the inputs are not numbers, but they're functions. Okay, and so the idea is, well, if we plug this number, this equation into this thing, do we get a true statement or don't we? Okay, so let's try A. We've got x, and then we've got the partial derivative of x squared y cubed plus y times the partial derivative of x squared y cubed. What does that equal? Well, the partial derivative of this is 2x y cubed, so x times 2x is 2x squared times y cubed. Partial derivative with respect to y is 3x squared y squared, multiply it by y, we get 3x squared y cubed. Put it together, you get 5x squared y cubed. Does that equal f? No. Okay, it equals 5f. So this is false. So this is not a solution. Do B. Okay, x. What's the partial derivative of that with respect to x? Partial derivative of this guy with respect to x? 1. So we get x times 1 plus y. What's the partial derivative of this with respect to y? Still 1? Yep. So we get x plus y. Does that equal f? No. If the 1 wasn't there, it would. So B doesn't solve the equation. Let's do the second one. Okay, we get x. What's the partial derivative of that with respect to x? 2x. Get the hang of it. Plus y times the partial derivative with respect to y. 2y. So we get 2x squared plus 2y squared. Does that solve the equation? No. Okay. Hopefully, this is a test. You probably just write D and go on. But let's just show it. What's the partial derivative of that with respect to x? Down comes the power, which is 0.4. X 0.4 minus 1 times y is 0.6. Oh, this x, put it in here, and then we get rid of the minus 1. Plus, okay, the partial derivative with that with respect to y. So what's the power? 0.6. X to 0.4. Oh, we've got to multiply it by y times y. Does it satisfy the equation? It does, right? Because we multiply by the y. 0.4 0.6. It actually equals. And so that's a true statement. So that solves the equation. Yeah, it's a lot of work. Not much, but anyway. Okay, so we can ask questions about from contour maps. So let's say we're at P. And we're interested in f, the partial derivative with respect to x. So what can you tell me about the partial derivative with respect to x? So if we go in this direction, are we going uphill or downhill? Uphill, so therefore the fx is positive. I'm interested in fxx. So what does that mean? That means the rate of change of the rate of change. So as we go up, is the rate that's getting, it's going up, Is it getting steeper as we go along, going in this direction? Yeah. That means it's positive. What about Fy? At first, the sign of Fy, we're going in this direction. So Fy is what, positive or negative? It's negative, right? Because as we go this way, we're going down into the valley. Okay, and what does Fyy mean? Fyy means it's going down. Is it going like this? In which case Fyy would be negative, or is it going like this? Which means Fyy would be positive because it's getting less steep. So what do you think is happening? It's definitely not getting, I don't think it's, we should get an edge. That looks like, the second one looks further, second contour line looks further away than the first contour line, doesn't it? It does if you put the edge in. Okay. So I think it's more like this. The Fyy is positive. A much harder question is, what's the sign of the mixed partial? So what does that mean? So here, okay, we're going in this direction. Things are increasing, but what happens as we go up here? So as we go up here, what happens to that across there? Are the lines getting closer and closer together when you go further north? It does. That means that's going to be positive. So if you think of it in terms of terrain, you can quite often answer these questions. I think we've got time for one last one. Let's go to a different point. At Q. So we're here. Okay, so this is kind of going up here. There's a hill there. So as we go in this direction, we're going uphill. So Fx is positive. What's Fxx? Is it getting steeper or not as steep? It's negative, right? Because we can see here, right, the whole things are close together and they're getting further out. And so that steepness is sort of going down. So it kind of looks like this. Okay. And then Fyy, what's happening there? So Fy, as we go in this direction, well, it's hard to say. As we go in this direction, it's getting steeper, so Fy is positive. But are they getting closer together or not? It looks like it's not. That looks negative as well. It does look like they're getting further away as well. How do you feel about that? Okay. So tomorrow we're going to have the last new material. We're going to have a look at